Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so we are thrilled to have Ricky Vora here. It's always wonderful when he visits. It was wonderful when he visited us in Redmond, and now when he visits us here. And you're going to be here through tomorrow or through tomorrow? Okay. And he's going to talk about optimal auctions for financially constrained bidders.
It's on. Right. Thank you very much. It's good to see so many familiar faces. This is joint work with Malaysia Pi, and for those of you who are counting slides, let me just say I don't intend to use all 31. By about slide 16, you can go to sleep. Beyond slide 16 will be some of the technical details, but the main qualitative points that I wish to get across, I will get across by about slide 16. Okay? Feel free to ask questions at any time. And this is joint work with Malaysia Pi, actually, who's now at the University of Pennsylvania, and who I think will be visiting MSR New England next week. Right. So what is the paper concerned with? It's concerned with the analysis of the optimal auction of a single object when agents have valuations and budgets, and both of those are private information to the agents. Okay? Now, you will notice I have used the more equivocal term analysis rather than the more definitive solve, and I'll explain why I've chosen the word analysis rather than solve, but it'll take me a couple of slides to get there. So why are we...
Analysis sounds more impressive, actually, so that may be why you chose it.
No, it also covers a multitude of sins. So it's, okay. So what is the motivation? The idea is, if you look at the standard literature on auction theory, it assumes that a buyer can pay any amount up to her valuation for the object. Yet there is at least a great deal of anecdotal evidence to suggest that that is not the case, that bidders have budget constraints that limit how much they can bid. Now, one can ask whether it is even sensible to live in a world where bidders have budget constraints, and there are papers that try to understand the source of the budget constraints, but that is not what we're doing in this paper. In this paper, we're taking the budget constraints as real, as given. A second issue is how you model the budget constraints. You have basically two choices. One is hard and the other is soft. In a hard budget constraint, the bidder simply cannot pay any amount that exceeds the budget. Okay? In a soft budget constraint, the bidder can pay up to the budget, but with extra financing can acquire resources that exceed the budget. So what you could imagine is that if the budget, say, is 200, any amount between 0 and 200 has a financing cost of 0%. Any amount above 200 would result in an increased financing cost to the bidder. So a payment of $1 above the 200 threshold is going to cost the bidder more than $1. Okay? That would be a soft budget constraint. That is not the kind of budget constraint that we're modeling here, for the simple reason is that that problem seems to be much harder than this one. Okay? Now, what is the novelty of the paper? The novelty of the paper is that the budgets are private information. So there is prior work which looks at the case where the valuations are private, but the budgets are known. And I'll describe some of that work a little later. Yes?
Are you going to both consider the hard budget and the soft budget?
Only the hard. In this paper, only the hard budget constraint.
So why not, if both valuation and the budgets are private, then why not just truncate the valuation at the budget? All right.
So the answer is, so you got to it very quickly. So the reason I had this slide is because after I describe the prior work, then somebody says, isn't it trivial? And my response is, okay, so my response is, I recognize the question, and so that you don't spin your wheels, it is not trivial. Okay, so in other words, this doesn't work. And a little later, I will give you a slide to show you why this isn't going to work. Okay.
didn't ask whether it's true.
All right. Well, he didn't ask her, but it was. Okay. Yeah. Yeah. So the first question is, okay, including budgets, does that make a difference? And the answer is yes, it does. You can easily think about standard auctions, and you can see that the presence of budgets would have two effects. They would reduce the possibility of an efficient allocation, economically efficient, not computationally efficient, and they will reduce revenue. Okay? And if this is the case, then a natural question to ask is, well, what other things can I do as the auctioneer to either enhance revenue or improve efficiency? And you can imagine a number of policy devices, and one set of policy devices that has been suggested is that perhaps if you were to subsidize bidders who are budget constrained, that would have the effect of either improving efficiency or increasing revenue. Okay? So the reason that we're interested in looking at the revenue maximizing mechanism is the following. What does that mechanism do to enhance either revenue or efficiency when bidders have budget constraints? Are some of the policy proposals, e.g. subsidizing bidders, is that what the revenue maximizing mechanism does? Okay? So the reason I want to emphasize this is we're not solving the problem because it hasn't been solved. We're solving the problem because we think it may tell us something about instruments that an auctioneer may use to enhance either revenue or efficiency. Okay, let me tell you about the prior work. You can divide, this is not a completely comprehensive list. You can divide it into two categories. In the first category are papers that do the following. You take a standard auction, English ascending, seal bid second price, seal bid first price. Now you endow the bidders with budget constraints and you ask, what are the equilibria of these auctions? And so that's what these papers do. So typically the result is some kind of revenue ranking that says in the presence of budget constraints, a second price auction perhaps generates more revenue than a first price, although I think I got that the other way around. Okay? Now some of these papers look at both hard and soft budget constraints. So for example, the Gavius, Sella, and Moldovanu paper has soft budget constraints, whereas the Che and Gale has hard budget constraints. Now, these papers here, what they do is they look at various policy proposals that you could implement, typically involving subsidizing the bidders, and then argue that in a standard auction, the effect of that subsidy is to either enhance efficiency or enhance revenue. Okay. Now, the second block of papers are concerned with actual design. I wish to design the mechanism to achieve a certain objective, knowing that the agents have budget constraints. So Lafont, Robert, and Maskin look at the auction of a single object when all bidders have exactly the same budget, and that budget is common knowledge. And Lafont, Robert look at revenue maximization, and Maskin looks at constrained efficiency. Okay. There's a paper by Alexei Malakov and myself, which is the same environment as this, except one bidder has a budget constraint and the other one does not. But again, the budget constraint is common knowledge, and the identity of the budget constrained bidder is common knowledge as well. Right? Che and Gale have a paper with a single buyer, where both the valuation and the budget are private information, and they look at the revenue, and they examine the revenue maximizing mechanism. Dobzhinsky et al. Have common knowledge budgets. Valuations are private, but they're not interested in either efficiency or revenue maximization because they wish to dispense with the Bayesian assumption. So they have a weaker requirement that the allocation should satisfy a Pareto condition. And then there is a paper by Christian, Jennifer, Mohammed, Madian, and I forget one other, Nicole, which looks at an environment with where both the valuation and the budgets are private information, and now, but the design is interested in a worst case measure for the auction. Okay. So the paper that I'm summarizing today has more than one bidder. Valuations and budgets are private information. They are drawn from a distribution, so I'm working in the Bayesian framework. and we're doing both revenue maximization and constrained efficiency. Although I will focus only on revenue maximization. Yes?
Chain gale is that you're going to have multiple buyers.
The difference between chain gale is we're going to have multiple buyers, yes. Okay. This is your question. A natural thing to think about is why not just have bidders submit the minimum of the two? This is not the correct answer to the question, and I will give you an example a little later on to suggest why it's not correct. But for the moment, take it as not correct so that you don't spin your wheels while I describe the notation. So let me introduce the notation, and then then I will state precisely the problem that we're going to solve. Okay? So we have one indivisible good for sale. We have n bidders, and the private information of a bidder is two-dimensional. It is valuation and budget. So this is the bidder's type. Okay? Each buyer's type. Could the budget be larger than the valuation? Yes, the budget could be larger than the valuation. Okay? Each bidder's type is an IID draw with a common prior density and over some space of types. Okay? And now here is the definition of utility. If your type is V, B, and you get the object, and you are charged a price P, and P is less than or equal to your budget, this is your net utility. If the price exceeds your budget, this is your net utility. This is the hard budget constraint. In other words, if you are asked to pay more than your budget, I shoot you. Okay? Right? Now, you could ask, is this reasonable? The answer is no, it is not. Okay? But why do we need to make an assumption of this kind? Well, supposing you were to run an auction and you were to hand the object to the winner of that auction, and that winner were to subsequently say, I don't have the money. What are you going to do? Okay? So the answer is, since this is a problem we don't want to deal with, we have a simple solution.
I remember there was a case in Spectrum auctions where it happened, and actually they gave the item to the next bidder, and then actually the one who won but didn't have the money said, that's not what you specified, I want the frequency and I'm only paying my budget.
That's right. So
it took a while to sort it out in court to not have to give it to
right, and there's another problem, which is what if you assign it to the winner, and then the winner subsequently declares bankruptcy? Now, who has priority over the asset? Okay, this is so this is a long-winded way of saying at some point you have to deal with the issue of what happens if a bidder says that they do not have the money to pay, and we're taking the simplest solution. Okay? So how about the indivisibility? So indivisibility is not an issue because I mean, I did indivisible goods, but you'll see the mechanism may involve some randomization. You can interpret the randomization as allocating fractional amounts of the good. So it's, okay. Now, by the revelation principle, we can restrict attention to direct revelation mechanisms. And so I'm going to be working in what is known as the reduced form. So this is the part that's a little tricky. So if you announce that your type is V, B, this is your probability of getting the good. And this is your expected payment. Now, the problem with the reduced form is that the reduced form does not explicitly specify the actual allocation rule. So let me unpack the reduced form. Strictly speaking, if I were to describe a mechanism would be first an allocation rule that specifies the probability that you get the good as a function of the reports of all agents. So let's suppose 2 agents, and let's look at Mr. 1. So the allocation rule would say this is the probability that Mr. 1 gets the good if Mr. 1 says his type is V1, B1, and Mr. 2 says his type is V2, B2. Now, from Mr. 1's point of view, the expected probability of getting the good is this, where this is the probability that Mr. 2 has this particular type. And so that A that I've written up over there is this. That's the reduced form.
So that's even a bit more complicated in that that's the announced type, right?
Okay, so that's the, right. So, because I'm going to impose incentive compatibility later on, I can assume that this is the other bidder truthfully reporting. But in the absence of incentive compatibility, you're right, this would be even harder to interpret. Okay? So the point is, I'm working with the reduced form. Now this raises two questions. If I give you a bunch of numbers for the reduced form, how do you know that there exists an allocation rule that satisfies this? And the second is, if I give you a bunch of numbers for the reduced form, can you easily recover what the underlying allocation rule is? Okay? It turns out both of those will be easy to deal with. Okay? And the expected payment is also in the reduced form. Okay? Now, the advantage of the reduced form, as you will see, is it makes the algebra for the analysis tremendously easy.
So there's one thing which I wonder how that would be covered in there. One way to deal with budget for me would be, for example, say, I do the following. If your valuation is higher than your budget, I give it to you with a probability which will make me if you get it, actually you sort of pay your budget. But I make the probability low enough that in expectation things work out. And how would I see that in here?
You're going to see it when I write down the formulation now. So I'm going to write down a formulation of the problem with all the inequalities, so you will see exactly how I'm incorporating the budget constraint. Okay?
So he's talking about an expected budget.
He's going to write. So one of the issues,
I said I never charge you more than the budget, and I make sure. And
I see, got it, yeah.
So your mechanism is not exposed individual rational, right? It's interior.
it is going to be, so because I'm working in the Bayesian framework, I'm only going to impose interim individual, right, so expected surplus should be non-negative. But let me put up the formulation. Okay, before I do that, now let me explain why it's not trivial. Why it's not trivial. So so let's look at the case where the budget is common knowledge. So everyone knows what the budget is. Then you might say, well, in that case, why not treat everyone's private information as really just the minimum of their valuation and their budget? And now this is a one-dimensional private information problem, and we know how to solve that from Myosin. Okay? So here's an example. Let's suppose two buyers. Valuations are drawn from the interval 0 to 1, and the budget is 0.5. Okay? Now, if you assume that for both buyers, if you assume that that the type is now simply min of v comma b, essentially what you're doing is you're saying the types are really all just between 0 and a half. Okay? Now the half number is critical because those of you who've done the calculation in Myosin know that when valuations are uniformly distributed on the interval to 0 to 1, the virtual value of a half is exactly 0. And so in Myosin, you never allocate to anyone with a valuation less than a half. Okay? So if you now applied Myosin to this, the Myosin auction would have an expected revenue of 3/8. What is its implementation? Well, one implementation is as an all pay, which is the following. If you announce a valuation that exceeds 0.5, this is your expected probability of getting the good, and you always pay this. Now, the thing to observe is that this is less than the budget. So you're getting the odd feature that if you simply did min of v comma b and then did the straightforward thing with Myosin, you would get a mechanism where no one ever pays their budget. And that should immediately raise suspicions, because if you know that someone's budget is a half, there must be there must be situations where you should be able to extract that. Okay? Yes?
When we look at min VB, the distribution is not continuous anymore, right?
There's going to be a mass at a half, right?
Does that violate any of the assumptions in Myosin?
No. Myosin works whether it's continuous or discrete, type space or a mixture. Okay. There is nothing in Myosin that relies on continuity. You can.
You should really be doing Myosin on some other conditional distribution, right? That's sort of why this is wrong.
Yeah, once you see the analysis, you will see what's the extra wrinkle that you have to introduce. Okay? And so in fact, actually, the analysis that I'm going to do is going to be with discrete types. And the reason for that is I can then set up the entire problem as a linear program. Okay? Now, if you object to the discrete type assumption, I have two responses. Response number one is I don't care. Okay. That's it. Right. I should remember that one. But the second is that just take the width of my discrete types to 0, and the discrete solution converges to the optimal solution to the continuous case. So in fact, one of the things I would argue sort of as a sideline is you should think about doing auction design with discrete types rather than continuous types, because one can use the machinery of linear programming rather than optimal control. Okay. Yes?
So here you don't know the literature of anything. Just in this case, the mean VB, if you do the second price, don't you expect to get F in both valuations of F?
Yeah.
So what's the problem?
No, the problem is simply if your intuition is why not just pretend everyone's type is min v comma b and apply Myosin?
I don't know what Myosin is.
So Myosin is the revenue maximizing auction when the valuations are private information and bidders do not have a budget constraint.
But there are other ways of doing it, right?
Well, so there are other ways, but they would all generate the same revenue as Myosin. In other words, Myosin finds the revenue maximizing auction, right? So what I did here was I simply did the naive thing, which is if I'm going to pretend that the private information is one-dimensional, there is now no budget constraint. What is the revenue maximizing mechanism?
You should tell them about the revenue equivalence principle.
Right. Well, you got to be careful. Even without invoking the revenue equivalence principle, it's simply that if I wanted revenue maximization, I should be using Myosin. Well, no, but your observation is, wait a minute, in this environment, there's another mechanism that could do better. And that's my point, that the naive approach cannot generate the revenue maximizing mechanism. Okay.
So the second price option is not guaranteed to maximize your revenue. It's guaranteed to do something else.
Right. Yeah. So here is the problem written down. So let me start at the bottom. So my variables are the interim allocation probabilities. That's the reduced form. And notice I want these to be feasible. What does it mean to be feasible? It means that there exist actual allocations consistent with these.
Is that a linear constraint?
Well, so notice I've labeled this border, and that's because there is a collection of linear inequalities due to Kim border that allow me to describe these. Okay? Now, okay, over here I have put down. Okay.
Proper nouns and common nouns.
Yes. Right. Yes.
This seems to be private knowledge.
Right. Okay. So right. So, or the other answer is, for the moment, I'm not going to say how I describe this. I'll talk about how to describe it later.
Who's Mr. Budget?
So here is the budget constraint, and I'm posing it as your expected payment is less than your budget. Now, at this point, you might be concerned and say, well, if the expected payment is less than your budget, then you're assuming a lottery over payments, and there is a possibility that with positive probability, you could be paying more than your budget. But the easiest response is, well, if I simply run the auction as an all-pay mechanism, then I take care of the ex-post budget constraint.
So what's all pay?
So all-pay is whether you get the object or not, this is what you pay.
You want to buy a house, you and everybody else pays, and the highest bidder gets it, but your money is gone.
Right? Now you could say, why would I participate in such an auction? Well, notice the constraint I put up here. Your expected value from getting the good minus your expected payment is non-negative. So if you are risk neutral, then the fact that I ask you to pay whatever happens, whatever the outcome, is not going to matter to you because of this constraint. Okay? So this is the individual rationality constraint, and notice I'm doing here the interim. Right? Now look at the incentive. Now look at the incentive compatibility constraint.
So why is it interim? So it's not ex post. That's clear.
It's not ex post. So you know your type, right? You know your type, but you don't know anyone else's type. Okay.
So if you look at the assumption of indivisibility, it would be exposed, right? If you interpret the probability of allocation as different.
If you interpret the probability, yes. So if you interpret these as probability, if you interpret the A of V comma B's as probability as fractions rather than probabilities, then you would get the ex post.
Yeah. You need more constraints, right? So this is for all the possible values that you can have, like all types.
This is for all types.
No.
Right, so I haven't put down, the for all, but the implicit is for all types, this must be true. For all types, this must be true. Now, where is the difficulty? It's the budget constraints. Okay? So, and they factor into the incentive compatibility. So now here is how the incentive compatibility works. Over here, I have got your expected surplus if you report truthfully. Now, over here, I should have your expected surplus if you misreport. But the budget constraint means what? If you misreport to a type where you are forced to pay more than your budget, well, you would never do that because I shoot you in that case, right? So I do not have to impose that incentive compatibility constraint. I only need to impose incentive compatibility constraints on pairs of types where the misreported type produces a payment that is less than your budget. Okay? So notice this is greater than or equal to this whenever this characteristic function is 1. Okay? Should there be...
So the whole thing...
It doesn't matter. You could put it down around the whole thing or around one of them. But the thing you should be worried about is this. Notice I am saying that you would never pretend to be a type whose expected payment is less than the budget. Notice what I'm ruling out. Supposing by misreporting, you would get a lottery whose expected payment is less than your budget, but with positive probability, you would have to make a payment that exceeds your budget. By my definition of the hard budget constraint, you would never lie to that, right? So I am imposing, if you like, more incentive constraints that I really need. So you could argue at this stage that I'm actually not solving the problem I claimed, I'm solving a more restrictive problem. However,
so is the all pay, can you always implement this as an all pay?
Any mechanism can always be implemented as an all pay if you have the expected, if you require only expected surplus be non-negligible. So that is one response, but as I said, some people could argue you're giving up some juice in terms of for the mechanism designer, right? Because there are some types, right? Okay. So the answer is the following: the program as we've written actually solves 2. That I'm really imposing this constraint: your expected payment is less than your budget. You could ask, you want to solve this, that the ex post payment cannot exceed your budget. But what we show in the paper is if the valuation and the budget are independent of each other, then the solution to this is also a solution to this. Okay? And if valuation and budget are positively correlated, the solution to this is the solution to this. But if they're negatively correlated, these two are different. Okay? Okay? So valuations and budgets are drawn independently of each other and independent across the agents. And so what we're really solving is this along the way we solve this. Okay? And now I can explain why I use the word analysis rather than solve. If my only objective was to solve, the talk would stop right here. I put up an optimization problem, feed it to your favorite solver. Okay? That's not what we're interested in. What we're interested in are qualitative properties of the optimal solution, which is why I chose the word analysis rather than solve. Okay? Okay. Now,
what if I don't like all pay? If I only like all where I...
It's a harder problem. So you're now asking basically, I don't like this version of individual rationality. I want ex post individual rationality. Okay. Now, here I set it up as maximizing expected revenue. If you wanted to do constrained efficiency, that would be your objective function. Yeah. I'm assuming all agents types are drawn from the same distribution. Yeah.
I mean, can you do something when there are several types of people?
Drawn from different distributions? The answer is, so the analysis I'll put up goes through even for that case. So from the point of view of the mechanism designer, in some cases you would get more revenue, but in terms of the analysis of the problem, it stays the same. Okay. And so it's just notationally convenient to assume identical distributions across all types.
And there are n players.
There are n, right. But the beauty of the reduced form is, notice, nowhere do you see a parameter counting the number of agents. Why is that? Well, because first of all, I'm making an assumption you might find objectionable, but can be justified, that the optimal mechanism is going to be symmetric. So it doesn't depend on the name of an agent. That's easy to argue. If it did, then flip the names. You get two different solutions. Take the average of the two solutions. That's also feasible. And so there exists a symmetric optimal auction. And because of the symmetry and because you're working with the reduced form, it allows you to reduce a problem from n agents to basically a one agent problem.
Wait. Why is that true that the average is feasible? Because this chi function...
You're right. It requires work. But that was just the that was the quick hand wave of why, as I said, you might find the symmetry axiom objectionable. If you did, we have a justification. But if it didn't bother you, don't worry.
So then that's sort of raising the question: is that even a linear constraint?
No, it's not a linear constraint. So this is getting onto the technical aspects. So in the case where the budgets are common knowledge, then it turns out that then the problem has a nice linear programming formulation, and the argument that I said goes through. But once the argument goes through for that, with a little bit of extra work, you can make it go through for this case.
So it ends up being convex.
It's actually a union of convex sets, and then you have to be very careful about how you do the switching.
So, and can my favorite solver I feed it to has no problem with that?
No, I cannot speak for your favorite solver, okay? But remember, for the economist's favorite solver never has a problem. Right?
So you're telling me Starter can deal with it?
Starter can deal with it. Does Starter have a solver function? I don't think so. Right? So, but if you're worried about solution, basically the guts of the proof basically show how to reduce this to a finite number of linear programs. Okay, and so that even though it's a non-convex feasible region, we can solve it as a finite collection of linear programs. Okay, now what I'm going to do is I am going to describe qualitative features of the optimal solution, and I'm going to do that by contrasting it with the optimal solution from Myosin. So recall, Myosin gives you the optimal auction when there are no budget constraints and only the valuations are private information. Now, how am I going to describe the solutions? I'm going to describe the solutions in terms of the behavior of the expected or interim allocations as a function of the types. So I'm not describing the solution in terms of the actual allocation, but in terms of the reduced form. Okay? So let me start with Myosin first. So worry about that later. So Myosin, supposing we had two bidders, and bidders' valuations were uniform from the interval 0 to 1. On the horizontal, I have valuations. On the vertical, I have the expected probability of winning the good. So in Myosin, if your valuation is 0.5 or below, the expected probability of winning the good is 0. At 0.5, there's a jump, and then the good goes to the agent with the highest valuation. But because of the uniform distribution assumption, that's the 45-degree line. So notice there is a reserve price below which the good is never allocated, above which the good is always given to the agent with the highest valuation. In other words, Myosin does the economically efficient thing above the reserve price. Okay. Now, what's the next level of generality? Supposing we give every agent a budget constraint, and it is the same budget constraint B, and everyone knows what B is. That's the next simplest case to look at. Now, what would we expect? Well, at some point, if the valuations get too high, they exceed the budget. At the point at which they exceed the budget, you cannot distinguish between two agents. Because the usual way we distinguish between one agent who claims a higher valuation than the other is by saying, in that case, please pay more. But since we've hit the budget constraint, we will reach a point where we cannot distinguish between two agents with relatively high valuations. Then what are you forced to do? You essentially are forced to treat them equally. So what would we expect to see? At relatively high valuations that would depend on the budget, this should flatten out. Does that make sense? We should still expect to see a reserve price below which we don't allocate. Now the only question is what would happen in between? And the natural conjecture would be that in between we should give the object to the agent with the highest valuation. Okay? So here is the picture for the case where you have two bidders, valuations are uniform on the interval 0 to 1, and both have a budget of a half. There is a reserve price. Notice the reserve price is lower than in Myosin. In other words, you might allocate to someone with a negative virtual value. Above some threshold, you're pooling. All agents with valuations above 0.7 receive an equal probability of getting the good. And in between, you give it to the agent with the highest valuation. Right? This result...
Is that a simple function of the two? Of the 0.5?
The two thresholds, yes. So there is an equation which I will show you, which is in general not a nice linear equation, but there is an equation which you can solve to find this threshold and this threshold. The real difficulty is this, the claim that you do the efficient thing in this interval. That claim is false in general.
Is that the 45-degree line?
That's the 45-degree line. So this is the solution claimed in Lafont-Robert. In Maskin, where he's looking at efficiency, the only difference is you take away this and this goes down. Both of those are correct only for the uniform distribution. Okay? If you move away from the uniform distribution, this is what the optimal allocation could look like. In other words, there's a reserve price. There is a threshold beyond which you pool, but in the intermediate region, you can do more pooling.
So we're still talking about the uniform distribution, or we're not?
This is still valuations. Oh no, I'm sorry. This should not be uniform. This should be any general where any distribution whose density is not decreasing. So in other words, this solution is only correct when the distribution of valuations satisfies the monotone hazard rate condition and has non-decreasing density.
The next one.
The next one, right. So the so this is correct only when you have decreasing densities and the monotone hazard rate. Drop the decreasing density, you can have pooling in the middle. Yes.
In that sense, it looks like we did some sort of ironing argument.
Yes. So all the pooling is coming from ironing. Yeah.
So that's a decreasing density. So if you don't have a decreasing density, it still might be possible that there is no pooling, right?
Yes. So in other words, yeah, you can certainly construct an example of a monotone hazard rate that violates the decreasing density, which you would not get pooling.
So it's a necessary condition. So it's a sufficient condition for not having pooling.
Yes. Yes. Decreasing density is a sufficient condition for not having pooling. It is not a sufficient condition. But now, if you think about it, I want both monotone hazard rate and I want decreasing density. You know, what satisfies that? Uniform, exponential, and things that look like the exponential from far away, right? So, okay.
Monomials?
Yeah, you can certainly get distributions to satisfy both those conditions.
General polynomials?
Benny Moldovanu has a list of what he claims are interesting distributions that satisfy both of those conditions.
We just learned
Okay.
about polynomials.
What's it?
About polynomials.
Polynomials.
So he's sharing his
Okay.
new knowledge.
Now I'm trying out as other people know.
So now let's look at a case where budgets are private information as well. And I'm going to assume that there are just two possible values for the budget, high and low. So there is a reserve price below which you don't allocate. There is a region in which you might allocate to the agent with the highest valuation. And then there is a threshold where all the low budget types are pooled, but you could still discriminate amongst the high budget types. Then there is a region where the high budget types are pooled. Okay? So to summarize, what's the difference?
Wait, are you allowed to distinguish now between low and high budget and not before?
Well, this is a notional example of the case where agents have budgets that are private information as well, and I'm only allowing two possible budgets, high and low. Right? Let's see. And so given the fact that in the population there might be two agents with different budgets, when somebody claims they have a higher valuation than another, it may be possible to distinguish between them. Okay? Now, the last thing you could ask is, in the optimal mechanism, are agents subsidized in any way? So the first is, you do not see type-dependent subsidies for the obvious reason that it's already incorporated into the model, right? The payments depend on your type. These could be positive or negative, so they could incorporate subsidies. You could ask about type-independent subsidies, flat subsidies. Okay? Now, when valuations and budgets are private information, and because everyone is drawn from the same distribution, it's not hard to see that flat subsidies cannot have any effect, because ex ante, all of the agents are essentially identical. However, when budgets are common knowledge and bidders may have different budgets, then the bidders look different. And potentially, offering a subsidy could make a difference, because the bidders you'd want to subsidize presumably are the ones with really tight budgets. What we can show is that the optimal mechanism doesn't do that. Let me be more precise. There is an implementation of the optimal mechanism that does not do flat subsidies.
So let me understand, does a subsidy mean an exception to the shooting rule, or what does a subsidy
So a subsidy would simply mean that I might announce anyone with a budget less than, say, 5, I'm going to hand them $1.
And then I only shoot them if they go over 6?
If they go over 6, right. Okay. So the optimal mechanism doesn't have to offer subsidies. So then the question that rises is, well, then what is it that the optimal mechanism is doing to boost revenue or efficiency? It's this pooling. So in effect, the way it is handicapping bidders is bidders are being pooled together, which encourages more competition.
So is it always the case that low budgets and high budgets are in different pools? Like if their difference is the difference in their budget is very small, couldn't be in the same pool?
Then they would be in the same pool, yes.
But they have different probability of winning.
They may I mean, this would depend on actually crunching the numbers for particular instances. This we've not done, right? All we're able to do, say, analytically, is that the optimal mechanism doesn't have to offer flat subsidies to bidders. In other words, there could be an implementation where that happens, but it is not a necessary condition for an optimal mechanism. Okay. That's the end of the qualitative highlights of the talk. So the rest is just what is it that we do to get the answers. Yeah.
Can I just go back to this example where, the first example where we,
this one.
The one after, I guess, or maybe, so this is your solution.
Yes.
And, so roughly, why didn't we take the minimum of the valuation? The budget is saying, okay, look, firstly, we should take advantage of the fact that this could be included as part of the bids.
Yes.
So there, And so do we see an effect of people who are posting two different valuations, both of which are higher than the budget? So somewhere your mechanism has to distinguish between these two types and change something.
Right. So this is the example where the budgets are common knowledge, but here I'm assuming they have exactly the same budget. Okay. So where is the budget? So where is the budget? Where is the introduction of a budget making a difference? The fact that you see the pooling here, that's not so surprising, because at some point, if both our budgets are 2 and you claim to be 5 and I claim to have a value of 6, there is no payment that you can ask of any of us to distinguish. Right. What's interesting is, notice over here, the reserve price actually falls compared with Myosin, where there is no budget constraint. Now, what this means by making the reserve price fall, I'm actually allowing bidders with small budgets a greater chance at getting the object. Now, why am I doing that? It puts competitive pressure on the bidders with the large budgets. Right? Because the thing you're worried about is the following. You have a large budget. Jennifer has a small budget. There's a limit to how much competition she can put on you. But one way I can encourage the competition is by essentially subsidizing Jennifer, not through subsidies, but by a more favorable allocation. Right? Yes?
I improve my chances of getting the good by saying that my valuation is 1 rather than 0.6. Even though I know I'm never going to be asked to pay more than 0.5, so why wouldn't I do that?
Well, notice, if you announce that your valuation is 1, all bidders whose valuations are in this range get exactly the same probability of receiving the good. So you don't change your probability of getting the good.
No, but if my real valuation is 0.6,
Yes.
then I have a lower chance of getting the good than if I say it's 1.
Well, notice what I'm graphing here is not the actual probability, but the expected probability of receiving the good. Right? So now if you say you're 0.6, this is your expected probability of receiving the good, agreed? But notice if you say instead your is 0.7, your expected probability of receiving the good goes up, but what do you think happens to your payment? I haven't graphed your payments here, right? So the answer is, in the complete mechanism, your payment would also go up, right? As I said, I'm only describing how the allocation probabilities vary with the reports. I'm not saying anything about what's happening to the payments, but the answer is payments will be monotone with valuations. Okay, does that?
So I guess another way of thinking of it is he already had that first constraint, which said that you better report 0.6 if it is 0.6.
Yeah, so this is the allocation subject to incentive compatibility. That means in the background there are payments that I can construct which give you the incentive to truthfully report 0.6. Okay.
Another question. I don't quite remember my Myosin in the sort of non-smooth cases, but I seem to vaguely remember that there's some pooling there as well.
No, okay. Under the monotone hazard rate condition, there is no pooling. That's why here I'm doing all of these with monotone hazard rate. If you drop the monotone hazard rate condition in Myosin, then you get pooling.
How is your pooling related to that?
So you will see that once I show you the analysis. So here, if you like, what we're saying is in Myosin with monotone hazard rate, there was no pooling. What we're saying is with monotone hazard rate and budget constraints, there is pooling. If you want to get rid of the pooling, you have to make an additional assumption, which is unappetizing, which is that the densities must be decreasing. Okay. Now, in terms of the underlying mathematics, I'm only going to look at the simple case where all bidders have exactly the same budget constraint, and that budget is common knowledge. Now, you could argue, why is the common knowledge budget constraint of interest at all? Well, if you were to ask bidders to post a bond, and the rule was you cannot pay more than your bond, it's not hard to show it is incentive compatible for the bidders to post a bond equal to their budget. Now, notice we're making an assumption here that you cannot go to a friend and say, give me some money and let me stick it in the bond. Okay? So if you're going to ask bidders to post a bond, then it would be reasonable to look at the case where the budgets are common knowledge. Right? So I'm going to look at the, yes?
In real life, it's not a good example, right? Because if I don't want to tell how much money I get, it may affect my valuation of the product if I have to declare.
Well, so most large-scale auctions will typically ask you to put down a deposit. And there will be a rule that says that your bid cannot exceed some multiple of the deposit. And if you want to raise your bid, you've got to increase your deposit. So as a result, and so yeah. So the
You don't buy Spectrum?
right, yeah. So asking bidders to put down a bond is not entirely unreasonable, but you could argue it's but a bond equal to the total payment up front. That's kind of a problem, right? So yes.
You make the same budget come now with the assumption just for the presentation?
Just for the presentation, right? And basically what it turns out is once you understand that case, it turns out the other cases are just easy. Okay. So let's first look at the problem with no budget constraints. So remember, valuations are private. There are no budget constraints. Maximizing revenue, subject to incentive compatibility, subject to individual rationality, and I want the interim allocation probabilities to be feasible. So what I'm doing is revisiting Myosin. Okay? So now what does Myosin do? Myosin says we've got two sets of variables, A's and P's. Let's eliminate one of them. So with some algebra, you can write the payment variables as a linear function of the allocation variables. And here it is for the discrete type case. Now there is a constant term which Myosin argues should be set to 0 in order to satisfy individual rationality. If you didn't set it to 0, it would be like allowing a subsidy. Okay, but let's just set it to 0. For those of you who prefer the continuous type case, wherever you see a summation, replace it with an integral. Okay? Now, if you plug in that expression into the objective function, grind through the algebra, this is what the problem reduces to. I get this coefficient here, which is called the virtual value, and incentive compatibility goes away. Why is that?
Little f of v or not?
So big F of v is the distribution, that's the density.
Yes, but in the discrete case, you have to tell me whether it contains f of v or not.
Oh, so so big F of v contains little f of v. So it's the sum of all things less than or sum of all probabilities less than or equal to v. Right? Now incentive compatibility goes away because in Myosin with one-dimensional types and because valuations are linear in your type, that's equivalent to requiring the allocation rule be monotone. Meaning, the moment you give me an allocation rule that is monotone in valuation, there exist payments that satisfy these inequalities. So now I get a simple optimization problem apparently. Maximize a linear function of these, subject to monotonicity, but I have not described feasibility yet. Right? So let me describe feasibility. This is from Kim Border. I'm going to write nu of v for virtual value. Actually, I'll worry about border later. Let's do budget constraints. So nobody can be paid more than budget. Right? Now, what can we say? Well, first of all, because of everything goes through, incentive compatibility means monotonicity. You can write down the payments as a linear function of the allocations. And because payments are monotone in allocation, you only need to impose this constraint for the highest valuation. Okay? Now, the other thing you can tell is because of the budget constraint, there has to be some valuation beyond which the payments are flat. So you might as well treat all valuations above that threshold as the same. So take the entire distribution and lump it onto this. So if you do that, you get a problem that looks like this. So this part is just Myosin. There's an additional part for the pooling at the top. Monotonicity. I only need to impose the budget constraint on that highest type. And I require this to be feasible. Okay? So this is the only wrinkle. Now let's get to feasibility. So border. Yeah.
At this stage, we're doing what you said shouldn't be done, right? I mean, it's like you're lumping all valuations above the budget as the same.
No, not all valuations above the budget. All I said was, I know there will be some V bar, right? I don't know what it is, but there will be some V bar beyond which they all make the same payments. So I just lump them together, and V bar will be a variable in the optimization problem.
Do we know that they're exactly going to pay the budgets for those types?
Yes. So the argument is that the only interesting case is when the payment is going, where the budget constraint binds. Because if it doesn't bind, we're back to the original problem.
Where do you see that the reserve price has changed?
You'll see that in a moment. Because
And this sum is only over V smaller than V bar.
yes, the sum is only over V strictly smaller than V bar.
And V bar could theoretically be still infinite.
Yes. Well, everything is say between 0 and between 0 and 1.
So do you know you have to pool at 1? I mean,
You could potentially pool at 1. All you know is you have to pool somewhere.
so, but it couldn't be that you don't pool at all, that V bar is.
If you don't pool at all, then the budget constraint doesn't bind, in which case you're back in the Myosin setting. Right? So to get out of the Myosin setting, I'm going to assume that you pool somewhere. Yes?
So in the Myosin setting, is it clear that it has to be linear? Is it obvious or it
No, it requires some proof. The quick argument is basically this, which is if you fix this and you fix this, then this is actually these inequalities are the dual to the problem of finding a shortest path in a network. And so that means, so that right away says, well, wait a minute, the payments must be a linear function of the allocation rules. Right? Because you're going to be choosing the payments to maximize. So you're not picking any set of payments in the feasible region. You're picking payments at an extreme point of the feasible region. And that's the reason why you're getting the linear relationship.
Right, increasing and linear is not the same.
Okay, so you're getting the monotonicity from the fact that from the particular linear expression you can work out that the payments must be monotone in the allocations. Right? Now here is Border's theorem. So how do I know that a collection of interim allocations is feasible? The answer is they must satisfy these inequalities. Now notice, I have these inequalities for every subset of types. What is it? N is the number of agents. That's where the number of agents comes in. What do I have here? This is the expected amount of the good that goes to agents whose types are in the set S. Now what do I have here? This is the probability that there is at least one agent whose type is in S. Okay? So this is clearly a necessary condition for feasibility. It turns out it's also a sufficient condition for feasibility. If you want, all you're really doing is you're taking these equations and you're projecting out these variables. Right? Now what is remarkable is that this, as a function of the set S, is submodular. Which means, if I ignore this, I've essentially got a polymatroid. Now, this is from the independence of types, yes. It's the independent.
But all you need, as you said, is the inequality, and therefore...
Well, actually, wait. Even with dependent types,
You don't get the whole thing.
you don't get the whole... Yes, independence of types is crucial to get the polymatroid structure. Yeah.
So this is where it was the notation which forced you to make them identical. Otherwise, as long as they were product distribution.
No, if they were asymmetric types, there's a generalization in which this is still a polymatroid. Okay, but if the types are dependent, that's when this is going to break down.
Right. So any product should have been okay.
Any product should be. But if types are dependent, then we know from Kramer-McLean we can extract all the surplus, and therefore that case is uninteresting. Okay. Actually, let me be careful. We know from Kramer-McLean with no budget constraints. With budget constraints and dependent types, we're out of luck. So far. Okay. So this is essentially a polymatroid. Now, why is that interesting? We know exactly the structure of the extreme points of polymatroids. What are they? Pick an ordering of the variables, and then let's call that a priority ordering. The first variable in the priority ordering, A of t, make it as large as possible, subject to feasibility. Pick the next variable in the priority ordering, make it as large as possible, subject to feasibility. That gives us all of the extreme points. Now, we require an additional condition on this polyhedron, which is that it should be monotone. That means we throw away any priority orderings that violate the monotonicity condition. So that means all extreme points of this and this can be described in the following way. Assign a priority to all types with the following property. A higher type must get a priority no less than a lower type. In any profile, allocate to the type with the highest priority. That describes all extreme point allocations. And so with that bit of legerdemain, solving this problem is easy, because what do we know about okay, so now the only catch is, what do I do about this extra constraint? The answer is, we're going to take that into the objective function with a Lagrange multiplier. So these are the Lagrange multipliers for the monotonicity constraints. This is the virtual value. This is the extra term from the budget constraint. And now I've got the polymatroid constraint. And notice I've not put down monotonicity. So we're going to do exactly what Myosin does. Myosin has this problem without this. And he says, well, I'd like a greedy solution to solve this, and I want the greedy solution to give me a monotone outcome. Well, how do I get that? Well, if the coefficients are monotone, then the greedy solution solves the polymatroid optimization problem. What sufficient condition would make these coefficients monotone? Monotone hazard rate. So what do we need? We need monotone hazard rate plus an extra condition here. This is why I need the densities to be decreasing. Okay? That's the... exponential in what?
No. He's talking about economic efficiency, not computational.
Right. Oh, so well, no, but it's also computationally efficient, right?
Well, it is computationally efficient too, that's true.
Right. I described a procedure that is polynomial in the number of agents.
So T is the type, the number of types.
T is the number of types, so I have a problem. So the input size, so the input now to the problem is the number of types, agreed?
If the number of types is like 10,
yes.
then you get for every subset, so it's 2.
That's true, right? But because it's a polymatroid, it doesn't matter, right? Yeah. Right. So what is the adjusted virtual value? It's Myosin's virtual value plus an extra term. And so in order for you to get the nice solution of give it to the guy with the highest valuation.
So is it that eta over f that's your...
Yeah, that's the, okay.
So that's kind of like the shift in the...
That's the shift in the, right. And so if this is monotone, then the solution that I put up, which is, give it to the guy with the highest virtual value, is still correct. And notice, because of this extra shift, it means that the reserve price will actually go down. Okay?
Oh, and if this is not monotone, then you sort of...
You have to do extra pooling.
Use this pooling
Yeah.
to do the,
Yeah.
instead of the,
Yes.
what we call the Gibbs construction.
The Gibbs, okay. Or, yeah.
Maxwell
So
construction.
actually, it's a Lagrange
Yes.
multiplier for the budget constraint.
So eta is the Lagrange multiplier for the budget
So
constraint.
shouldn't that be minus eta over density?
I don't know. I guess it's going to depend on your convention. So my convention is to do right. I'm maximizing, right? So when this goes into the Lagrange multiplier, it's going to be eta multiplied. That's the way I'm going to put it up into the Lagrange multiplier.
Yeah, so when it goes in...
No, but remember, I then substitute out the payment variable, okay? And then the payment variable will look something like this. Okay? And, oh wait, did I get well, maybe I did get the sign wrong.
You want to...
No, I think I'm fine because
Because I think your visual valuation should be less than...
No, because it's going to be this. This is the constraint, right? Remember, I'm treating V upper bar not as a variable, but as fixed. So supposing somebody gives me the threshold, right? So then my constraint really, if I take the unknowns to the other side, will be like this, agreed?
Oh, okay. So you're assuming like inequality constraint, so your Lagrange multiplier could be either positive or...
It could be either positive, because,
Yeah, I was like, thinking that if you write it as inequality constraint, then it would be the other way. So
No, it would still be okay. Right? Notice the variables appear with a negative coefficient.
I guess the main point is that you're expecting the new virtual valuation to be smaller.
yeah, that is what I was thinking.
The new, well, no.
Smaller than the Myosin.
Yeah, that is.
No, the new virtual values have to be larger.
Didn't you say that the virtual valuation could become negative?
Yeah, so now notice it could require a smaller virtual valuation to make this term negative. Right? Because in Myosin, you care about when this becomes 0. Agreed?
So here you allocate it when the new virtual valuation is positive.
Is positive, right?
So, but the original virtual valuation could be negative.
Right, so this could be negative, but because you're adding an extra term, the new modified virtual value could be positive, right? Okay. So in effect, all that's happening is give me all sorts of side constraints you like on the allocation. Just stick them up into the objective function with Lagrange multipliers, call it a virtual value, and allocate to the object with the highest virtual value. That's the entire trick. Okay? Now, let me just close by saying, all right, I've given you one application of the use of the reduced form, which uses this polymatroid structure. What I want to convince you of is that this is not just a one-off. The polymatroid structure is useful in a number of other applications. So one thing that now becomes relatively easy to prove is the following. Bayesian and one-dimensional private information, allocation of a single object. This polymatroid structure allows you to prove the following. Every Bayesian incentive-compatible mechanism can be implemented in dominant strategies. Right? So in Myosin's original paper, that statement was only true for the optimal mechanism. This is now a statement about all Bayesian incentive-compatible mechanisms. And that just comes from looking at the extreme points of the polymatroid. Right? Second application is in a paper by ΓÇŷpoolingღö and others where they're interested in designing mechanisms that are what are known as cartel-proof. So again, they used the border polyhedron to write down a collection of linear inequalities, and because of the polymatroid structure, they can compute the solution and then describe the mechanism that is cartel-proof in addition to just simply maximizing revenue. Now you might say perhaps this is only useful for static environments. No, this idea also carries over to some dynamic environments with certain assumptions, because for banded problems, if you choose the variables correctly, the set of feasible banded policies live in what's known as an extended polymatroid that have essentially the same properties as polymatroids. And so under certain conditions, you can simply port the Myosin result to the dynamic case because you're working not with the actual policy, but with a reduced form of the policy. What is the reduced form of the policy? It's the expected discounted number of times you engage project I in state J. Okay? Let me now close with a notional picture of what the optimal allocation rule might look like if you have many budgets and many valuations. Let me just skip over the algebra. Here is a notional picture. So valuations on the horizontal, budgets on the vertical. And these purple pools represent pairs of types that are pooled together. So the allocation is monotone in this direction. All types that are in the same purple rectangle and oval receive the same probability of being allocated the good, and payments will be monotone in this direction. So if you decide to jump from here to here, your payment goes up. Now, the last point is subsidies. I said that the optimal mechanism does not offer lump sum subsidies. How do we get that answer? Well, let's go back to the case with a single budget constraint. If I offered a type of lump sum subsidy, that would have the effect of raising the right-hand side. Now, if I raise the right-hand side of a linear program, that increases the objective function value. The amount by which it increases the objective function value is the dual variable associated with that constraint. Well, we can prove that the dual variable, eta, is strictly less than 1. So therefore, you never subsidize. Yeah. And that same argument goes through in the case when there are many budgets. Okay. And I'm out of time here. I'm sorry to have run over.
No, you're fine.
So, okay.
Can I ask a question about the, so what happened to this one tricky looking constraint which you said, oh, this is not linear, but we'll get back to this?
Okay, so I described the solution when the budgets were common knowledge and everyone had the same budget. So now let's go back to the problem I put up to begin with, this one, right? So what we do in the guts of the paper is what we show is that there are a finite number of critical budgets, and you can and we don't know what they are, but let's suppose somebody handed us those finite set of critical budgets. Now solve the problem as if those are the budgets, common knowledge, and what we do is we enumerate over the set of these critical budgets. So that's
How do you, I mean, if you had a countable set of possible budget, you would have a hard time searching through that. So I would assume you do some kind of binary search or so.
Well, no, we take the cheap way out, which is, because remember, at the end, the goal was only to say something about the structure of the solution rather than compute it. So, and what we wanted to know was, does the optimal mechanism subsidize? So in terms of the analysis, it suffices that there exist a set of critical budgets.
Oh, so you might have to search through an uncountable space.
No, okay. Now, since we're assuming a discrete type space and types are bounded, right. Everything is countable, right? Okay. Now you might worry a little bit about, well, what about my throwaway remark earlier about taking the width to 0 and then claiming that, that the limits are all well behaved. Even that can be handled, but I have to be honest, at this point in the paper we got tired and we simply hand waved. But roughly speaking, the argument is that you know that discretizing gives you a subset of the optimal you're in a subset of the optimal space when types are continuous, and because of compactness and closeness, you know that the optimal solution for the optimal objective function value for the discrete case must converge to the optimal objective function value for the continuous case.
This is closed. It could be this discretizing maybe an open set.
Well, no. So we're going to assume that the type space is compact, and the discretization is simply, the obvious mesh.
But that could still mean that the limit point you get is sort of.
No, so we're optimizing a linear function, right?
Assume that the set is actually closed.
Yes.
But your set of solutions could still be open.
Okay, so let's be careful. So this argument only says that the optimal objective function values converge. It doesn't say anything about the solutions, right? Okay, so with the solutions you have to be a little more careful, which is you have to say, but wait a minute, I know that the solutions have to lie in one of these polyhedrons, and each of these polyhedrons must be in the feasible region for the continuous type space. And so by the Carathéa-Dori theorem, right, each of these is a convex combination of some of the extreme points in each of these subsets. So that means the weights on these things must also be well behaved. That is the hand wave. Okay. So I was careful to say hand wave, but for the case where budgets are common knowledge, the argument is there in the appendix. Yeah.
I have a different question, which is the one you said if you would, instead of doing intermediate individual rationality, you would post ex post individual rationality, you just got a tighter constraint. Does that mean you can solve this thing?
No, that's much harder, because the reason we can do everything here is because we're working in the reduced form. So all constraints can be expressed using just these variables. The moment you insist on ex post individual rationality, one has to work with these. That blows up the problem. And
it's left to the reader.
It's left to the adventurous reader. Yeah.
So is there a similar story for efficiency?
Yes. So the only difference with efficiency is you would replace this by A of V comma B, and the only difference would be there would be no reserve price. Everything else goes through, except there's no reserve price.
So it is some all-pay auction.
It is, so one implementation is as an all-pay auction, yes. Thank you.